Hi, we're going to look at quiz 2B question A. We start with a mass on a vertical spring. There are two versions of this quiz, but they're both pretty similar. We're going to do the first one where we push this mass. This is its equilibrium position. We push the mass 0.4 meters above the equilibrium position and we let go. We call that time t equals 0. The question states you measure the period of oscillation to be 2 seconds. What that means is I push it up here, this is 0 seconds, and then I let it go, and it goes down and up. That's one period of oscillation. That was 2 seconds. We call that the period. So I give you directly that the period is 2 seconds. The question says draw a graph showing the y displacement of mass versus time, and also write an equation. So if I draw a graph, at time equals 0, this is my time axis, this is my displacement axis, and at time equals 0, I start at 0.4 meters above equilibrium. That means I know it'll go down to minus 0.4 meters, and I know it'll follow simple harmonic motion. So we're going to start up here and draw a simple harmonic motion. I also tell you that the period of one oscillation, that means starts up here, goes down here, and up here, is 2 seconds. I'm done drawing the graph. That's all you need. I can also break this up or write other values on the x-axis. This is 1 second, 0.5 seconds, 1.5 seconds. Now we need to write an equation to describe this graph. The equation is just a cosine curve. And the general form of the equation is y equals a cosine 2 pi over the period times time plus a phase constant. I can just plug in the values because everything is pretty straightforward here. Y is equal to 0.4 cosine 2 pi over 2 seconds times time. And there's no phase constant. That is, cosine of 0 starts at the maximum value. And that's what I have right here. So I don't want to add a phase constant. I want time equals 0 to correspond with the maximum displacement. This is my equation. We can make sure that it corresponds with this if you want to plug in times 0.5 seconds, 1 second, 1.5, and 2. But I'm certain that will be the case. One of the quizzes said the opposite. They started by pulling it down 0.4 meters. So how would this graph look different if I pulled it down first? And the difference would be that my graph would start right here. And then it would go upwards and downwards and back there. Right away I can see the relationship between this and the original graph. The relationship is that I have a negative cosine. So I could just write y equals negative 0.4 cosine 2 pi 2 times t. That would be sufficient. Another possible way to answer it would be to say it's a cosine that has been shifted by some distance pi. The way we would write that equation is y equals 0.4 cosine 2 pi over 2 times time plus pi, or minus pi. Either way would work. These two equations are equivalent to each other. For the second part of this equation, I said, or for this question, I said, I take my mass and I make it 1/4 of its original mass. The other class said I take my mass and I make it 4 times the original mass. So how is it going to change this graph if I change the mass? If I make the mass lighter, I expect it's going to move up and down more quickly. So if I make the mass lighter, I expect my period will be shorter. While if I make the mass heavier, I expect my period will be longer. But if I do the same displacement, I'm going to have the same amplitude. How much does the period change? Let's start with the first situation. So we have mass 1. I'm going to do this in red, so we stick with class 1. Mass 1 is some mass. Mass 2 is equal to 1/4 mass 1. We have an equation for the period. It's equal to 2 pi square root of mass over the spring constant. So if we have mass 1, let's call that period 1. We can also write period 2 is equal to 2 pi times the square root of mass 2 over the spring constant. Let's go ahead and plug in my mass 2 relationship to mass 1 so I can relate the period of 2 to period of 1. This is equal to 2 pi square root of 1/4 times mass 1 over k. So we could write it like that. I can take this 1/4 out of the square root because square root of 4 is 2. So this is equal to 1/2 times 2 pi square root of m1 over k. This quantity right here, this is equal to period 1. Period 1 is 2 pi root m1 over k. And so my final equation says that period 2 is equal to 1/2 of period 1. So that means if I put a lighter mass, it's going to oscillate more quickly because its period will be shorter. So I could draw on this graph again, and let me draw it with a dotted line. The period is going to be 1/2 of this. This had a period of 2 seconds, so this period will be 1. And if I draw it with a dotted line, I'll draw it better. Then it'll complete 1 revolution in half the amount of time. I could continue to draw this. My scale isn't perfect, but hopefully you understand what I'm trying to do. That's the answer to the situation where we make mass 2 1/4 of mass 1. Let's do a similar problem now, but with the other class where we make mass 2 4 times as big as mass 1. So we have some mass, mass 1. We have another mass, mass 2 is equal to 4 times m1. Again, we have this equation. Period 1 is still equal to 2 pi root m1 over k. Period 2 is equal to 2 pi root m2 over k equals 2 pi square root of 4 times m1 over k. Now I can take out this 4 from underneath the square root, and I have 2 times 2 pi square root of m1 over k. This quantity right here is equal to period 1. And so in this case, period 2 is equal to 2 times period 1. In my first situation, the period was 2 seconds. But now I'm saying that my period is going to be twice as big when I use a mass that's 4 times as large. So 1 second, 2 seconds, 3 seconds, 4 seconds is going to be the period for my heavier mass. I can try to draw it over this, and we'll see if I succeed. 2 seconds, 3 seconds, 4 seconds. That represents the longer period associated with the heavier mass. Now, you don't have to draw these to scale. You can also just change the axes so that the tick marks have different values of time associated with them.